Welcome to the PLC Professor's Workshop Lab. This is where we develop all of the lab projects with the hardware behind us. These days we spend more time working with the simulator, which does not require hardware. If you have Connected Components Workbench version 12 or later, at this time there is no later version, but when there is 12 or later, you have a simulator available to you. And in this lab project, although you can do it with hardware, we're going to be emphasizing the simulator and specifically the configuration of I/O wiring, which is a nice feature of the simulator. Now, this particular lab project, you might say it's the first one in part 2 of CCW, the 3rd edition. At the time of this lecture, we are just introducing the new Part 2, 3rd edition. And these are now two separate documents, Part 1 and Part 2. You could call them Semester 1, Semester 2 if you like, because they're both quite lengthy. And what we are going to do, because we are kind of running out of paper in the sense that both Part 1 and Part 2 have gotten well up over 250 pages. You know, they're approaching 300 pages. That's just too much paper. So we're starting to thin back on what we do in the lab projects. And for instance, this lab project, M38, with the 3 compressors and writing code to manage the budget of 3 compressors in a manufacturing facility to maintain air pressure out in production, but have 3 compressors so they can run in shifts, and then have one of the other 2 be the backup if the first one can't keep up, and then run in shifts with a budget. Because there are so many things that we can do with this lab, we've decided that we're going to keep it simple. We're going to stop it at some point. But in our lectures and discussions, we're going to explore some additional things that you could do in the lab. Now, I want to tell you up front that on some of these lab projects, specifically this one, if you're watching this and if you have not subscribed to the video subscription for all of the lab project discussions for Part 2, if you've not subscribed, then you will only see Part 1 of this lab project discussion. But I will still try to give you some valuable information in Part 1 so you don't feel like you wasted your time. But I'll just warn you up front. If you can't deal with the idea that you're not going to see the whole thing all the way through to the end and only part of it, then it would be a good idea to go on to something else and not watch this video. Because this particular one is just Part 1 of the discussion of that project. So let's look at the lineup for this project. This is the lineup sheet from the manual. By the way, these manuals are used in universities and colleges alike. When I said Semester 1 and Semester 2, Part 1 of this course, if you want to call it that, that is a semester. You can easily spend the entire semester on Part 1, and this would be Semester 2 or Part 2. This is the first project, and it's the compressor sequencer project, and this is the lineup sheet. We have 3 compressors, A, B, and C. Now, we do show some things that we may or may not use in the project. For instance, I show cubic feet per minute up in the diagram in the upper left-hand corner. The project in the manual does not include any analog or high-speed counter. That CFM, that could be a impeller type sensor, and you're getting back a pulse train and you're counting the pulses to calculate the cubic feet per minute. We do have a lot of enhancements that we can do with this project, including using analog instead of digital feedback sensors. Okay, 3 compressors, and they're all sized. Each one is sufficient to supply enough volume at the specified pressure, typically 80 psi, at the plant production area when they're in full production. And of course, we know that sometimes that's not enough to keep up. And we don't want to run one compressor 24/7, 7 days a week, week in and week out, month in and month out, because you need to shut them down once in a while for maintenance and or rebuild. So we have 3 compressors. Each one is capable of supplying the nominal amount of air volume at pressure for production. We're going to give each one of them a specific budget of time. Now, in the real world, it could be 3 hours, 6 hours, 8 hours, 9 hours, 12 hours, where you run A for 12 hours, then B for 12 hours, and then C for 12 hours. We're going to use something really short, like 12 seconds, simply because we don't have the patience to sit around and wait. Part of the lineup is that no matter which compressor is running, if A is running, then B is the secondary, meaning if A can't keep up, then B kicks in to maintain pressure. However, we want to accumulate the runtime on each compressor. If we are running A and we pull in B as the secondary, the time that B runs as the secondary counts against its total budget when it's the primary. And then when B is the primary, C is the secondary. When C is the primary, then A is the secondary. That's simple. If you look at the I/O down there, and this is just our suggested I/O. We have a toggle switch maintained to select manual or auto mode. And then we have compressor override switches for all 3 compressors, meaning that in certain situations you can flip the switch on and that compressor runs whether it's primary, secondary, or otherwise. Okay, we've also got an input low pressure and then another one low pressure. Now you'll notice that I skipped from 4 to 6 on the inputs. Low air pressure could be input 6 if that bothers you. When you're writing your code, you can just edit it so low pressure is 6. And both of these pressure switches or contacts are one sensor out in the production area. So if the pressure drops below whatever they think is the minimum, because you can't have the compressors cycling on and off for a change of 1 psi. So if it's set at 80 and it drops to 79, you can't be kicking it on and then back off at 80. You need a range where when it gets below a certain level it kicks on and it runs until it exceeds some higher level. So you have a span or a range there. Well, the low pressure would be if it drops so low that the equipment's going to start operating erratically because it doesn't have enough flow or enough pressure. And then we've got inputs 11, 12, and 13. These are outputs from the controller to tell the compressor units to run. So this controller that we're writing the code for is not the controller for the compressor. It's the supervisory control for the whole compressor room. When we want unit A to run or to be the primary, then we enable it. If it's going to be the secondary, we're going to do the same thing. So input 11, 12, and 13 are inputs at the compressors to tell them to run. Now you're probably thinking, well, wait a minute, shouldn't they be outputs? Well, we're going to do configuration I/O wiring diagrams in this, and you will see that we're treating this whole thing having 3 different complete separate locations. One is the supervisory control system. Then in the compressor room, we have 3 compressors. Each of those is an entity. The compressor will have inputs 11, 12, and 13 and outputs 11, 12, and 13. Meaning the compressor A, unit A, will have an input at its control saying to run. But it won't run. That'll just enable it. It'll actually take a low pressure ANDed with run unit A to get it to run. The supervisory control knows that unit A is running, then we have output 11, which is unit A running. So that's an output from the compressor coming back to tell us that unit A is running. The output from our controller that is the input to run unit A is output 1. So if you look down below, you see we have outputs 1, 2, and 3. Enable A, enable B, enable C. Now I know this is probably confusing right now, but you'll see when we get into configuration I/O wiring that this will all make sense. So notice we also have several low pressure and low pressure, and this will make sense. So let's move ahead here. Okay, first of all, we're going to buffer our I/O. These are buffered input states. What that means is that the very first program file in our program is going to take the state of the screw terminals, which updated, I/O embedded, digital input 00, all of those memory locations on the left side is going to copy those into the right side, IN00 through through IN27, because we're going to buffer all 27 inputs. I'm just showing you 7, just so you get the idea. And of course I have them labeled. So keep in mind, when you're writing code, it's much easier to type in IN00 than to type in underscore IO underscore EM underscore DI underscore 00. So we do two things here. First, we buffer the IO so we don't have to be concerned about the state of the IO changing during the scan of the program, and the other is to give us something easier to work with. We're also going to buffer the output states. Now notice in this case the secondary memory locations, OUT00 through OUT19, because we have 20 outputs on the simulator, that they are on the left side of the logic because we're going to use, as you see there, IN00 through whatever the highest used input is. We use those memory locations to read from, and we're going to write to OUT00 through whatever number that you use. So this would be the last program in your project, would be buffering the output states. What you're looking at here is a couple screen captures from the global variables. Now you notice that it's IN00 through IN27, that's 28 inputs, but these are the buffered states. These aren't the actual IO states, the screw terminal states. These have been buffered, but remember this is what we use in our programming. And then you see that we have 20 OUT00 through 19. And we have some aliases. You can use descriptions or you can use aliases. For input 0, auto manual switch, that is the alias for IN00. So I can program with auto man underscore SW or with IN00. Either one is that memory location that effectively is underscore IO underscore embedded underscore digital input underscore 00. There are a few here that I'm not using. In particular, remember we kind of skipped input 5 because that would be something we might do later to run the chiller. And that's something that chills the air in the compressor room to start counteracting some of the heating due to compressing the air. And then fault indicator output 00, and then output 4 run chiller requested. So these are a couple aliased IO points that we're not actually going to use in the primary lab project. Okay, this is a diagram of our system. And we're starting with the compressor room. We have 3 compressors, unit A, B, and C. We have a reservoir. You'll notice that there are a few things that are grayed out. Specifically the PSI in the compressor reservoir, degrees Fahrenheit in the compressor room, and degrees Fahrenheit on the intake air on the chiller. Those are not involved in this project at this point. We might explore what to do with those later on in our discussion, but in the manual you're not going to find them. However, we are using the PSW pressure switch from the production area. So we've got this divided up into, let's call it the supervisory control to the left that's grayed out, and then to the right the production area. And primarily we're going to start with the compressor room because these existed before we started this project. The 3 compressors were already there, but they were operated manually. In other words, someone in engineering or maintenance would manually go into the room, the compressor room, and turn on B and turn off A, and then sometime later turn on C and then turn off B. You always want one running before you stop the primary. We didn't necessarily address that in our program, but that's an enhancement that you can add later. So Looking at just the compressor room, and notice we got it labeled INs 11 and OUT 11. So you don't want to get too tangled up in this. Remember that we are simulating the compressors and we are simulating the production area. We're simulating this whole entire process. But in order to give you some nice, rich experience with configuration of I/O wiring, we're treating Unit A, Unit B, and Unit C as completely autonomous, isolated elements, which means that Unit A has an input coming from somewhere that says run a command. And then it feeds out a charging back to wherever run a command came from. Of course, you can see where it comes from. So you can see that run a output 1 goes to input 11, run a command. And then if it's running, and of course it's not going to be running unless it gets low air pressure. So just telling it to run, which is really an enable. So output 1 enables Unit A through IN11. It enables it, but doesn't tell it to run. It enables it. Low air pressure is actually going to tell it to run. We don't show that here. Okay, and notice that output 16 and 17 is coming from the production area and coming into input 4 and 6 in the supervisory control. Okay, the production area, we're going to have logic that simulates the production area. And of course, the production area is going to have air pressure that goes up and down. It goes up when the units are charging, down when they are being depleted. In other words, when you're drawing volume off of that main tank in the compressor room, the main reservoir, that pressure is going to drop. And when it gets down to, 7, 8, 9, 10 psi below set point, it's going to say low air pressure. If it keeps dropping, then it's also going to turn on low. Now I noticed that just now that I only have it low production pressure, I don't have low on 17, output 17. That's what it should be though. You see input 6 is low pressure. And then the supervisory control, looking at just it, okay, and this is, if you had a real application, this is all that you would have. You wouldn't have any of those other I/O because they are representing simulated loads and other control entities. We enable Unit A with output 1, and then Unit A comes back and tells us that it's running, it's charging the system. And then down below, of course, you have low production pressure, input 4, low production pressure, input 6. We've also got our overrides, input 1, 2, and 3. We've got our auto manual switch, and we have a push button for reset. So input 20, we are simulating as a reset push button. Now what you're going to do with that reset is going to be up to you. We're going to use it for something really simple. This is kind of a look at our project, but we're not going to look at the code in this first part. But I am going to point out in our organization of programs, you've got buffer inputs and buffer outputs. You've already seen some representative code for buffer inputs and buffer outputs. We also have system, which is what you're looking at in the code right here, where you have manual mode, auto mode, and then you have some reset. Okay, so there won't be a whole lot in the system code. I mean, there'll be more than what you see here. But the system code kind of is at the 10,000 foot view of overriding A, B, and C if you're in the manual mode, etc. And all the switches have to be off in order to get in and out of manual mode and auto mode. So you can't be flipping on compressor override switches and then changing modes. But that's part of the lineup. We also have production. Now, we're not showing any of this code. We're just talking about how we've organized our programs. That's where we have logic that when you enable consumption, in other words, let's simulate the production area, you're going to have timers that turn the low pressure off for some time while you're, consuming air, and then turn it back on to tell the compressors to run. Then, of course, we've got compressor A, B, and C. Remember, we're treating each one as autonomous devices. And so what you're going to have in these three programs is code, and all three of them are identical except for the memory locations. They're going to simulate the behavior of a compressor. And then, of course, all of this is controlled from sequence. And in the sequence is where we kind of watch how much of the budget for each compressor has been consumed. We select primaries, secondaries, and do switchovers. And then last but not least, we've got a very special program called HMI, Human Machine Interface, MMI. In other words, this is your screen that you can control the system from, and you can monitor what's going on. Now, this is not an HMI, for real. It's code, but it's laid out in such a way that it's really not controlling anything. It's laid out in a way that you can watch what's going on and you can turn things on and off. This is probably the more complex part of this project, and that is the configuring the I/O wiring. Now, in another section, we will probably run a video clip of the simulator actually running so you can see the outputs, inputs going on and off. This is the configuration I/O wiring. Now, you can only do this once you've instantiated the simulator. In other words, you told it to run, but you didn't power it up yet. Once you power it up, then you can't do this. So you instantiate or start the simulator, but you don't turn on the power to it. Then you can go in and you can associate output 1 with input 11. So if you look on the left, you will see that I've created a graphic. And if you look at the screw terminals, some are orange, some aren't. If they're orange, that means they're on. If they're gray, they're not on, or white. But you can see the little tick marks or pointers to the left or the right of the screw terminals. That indicates that there's some I/O configured wiring. And what I did was I drew in orange and brown lines to show you what's connected to what. So if you look at output 1, enable compressor A, that goes over to input 11, compressor A enable. And then inside the code for compressor A, if it's also seen input 4, low air pressure switch, which comes from low pressure switch, output 16, then that compressor runs. So this is the configured I/O wiring. Now I'm showing you over to the right what the chart looks like. Notice that digital output 4 to digital input 5 is not used. It's unused. We might use it later. Notice that there are no delays. This is another nice feature, is you can put in a delay between when an output turns on and when the input follows suit. Now we're going back to our global tag or global variable database for you to reassociate that screen capture with the configuration I/O wiring on the left. And same thing with outputs. And for your viewing benefit, we're going to give you a little video here, and you can see the inputs and outputs changing state. Now when you're running the simulator, if you mouse over any of the tick marks, it will pop up the wire. So you see that input 23 is connected to output 13 down below. And vice versa, you're going to see that on all these. So if I go to 6, you see that goes to 17, 4 goes to 16. If I go to 1, that goes up to 11. And right now you can see that 2 is on, so 12 input is on. This is because we're, see right here, we're running compressor B. So when you see enable compressor B come on, now it's going to be running C. See, so 3 goes to 13. So between this animated simulator and the HMI program, this is as good as you're going to get when it comes to doing this type of thing without actually having a hardware controller. So we're going to tidy it up here, and we'll pick back up in part 2 where we'll actually talk about the code that's going on in the background.